Okay. So in the previous class, we have completed till here. Now, that is the last part that we have to do. At molten magnesium, a molten magnesium salt is electrolyzed for 15 minutes by a constant current. Okay. 4.75 exponent 22 atoms are produced at cathode. Okay. Calculate the value of the current used. Okay. So if they have told us that magnesium atoms are being formed, so if the magnesium atoms are being formed, which means I can write that the reaction that is occurring at the cathode would be this one, right? And in this reaction, if we see there are 2 moles of electron, which means that 2 times 9.6500 coulomb charge is being used to form 1 mole of a magnesium, and the mass for the 1 mole of a magnesium would be 24.1 grams, right? And see here, instead the mass, what we have provided, we are provided with the number of atoms. So if we look into the number of atoms for this one magnesium, it would be 6.02. Okay, so here 2 moles of 96 2 moles of electrons are being used, which means to get 1 mole of magnesium atom, which means 6.02 exponent 23 atoms. Is this ratio is understandable to everyone? Then in the question, they have told us that the time for which the electrolysis is performed is 15 minutes. So I have to convert it into a 60. And when I multiply it with current, I would get a coulomb. So I don't know the current. I have to find the current. So that's why I put an I over here. For that, 4.75 exponent 22 atoms of magnesiums are being formed. So this is the relation that we have got over here. Is this clear to everyone? Now, if I have to find the value of current, so the current would be I is equals to 2 times 96500 multiplied by 4.75 exponent 22 divided by 15 into 60 into 6.02 exponent 23. Is this understandable to everyone? Yes. So can anybody solve me and tell me the answer?
The 16.9 amperes.
So we are getting 16.9 amperes. So the answer would be 16.9. Is this clear to everyone? If anyone have any doubt, do ask. Okay. Now, we have ended the question number 3. Now we are going to start with question number 4. Okay. Here, the value of the solubility product KSP of iron 3 hydroxide, and we have provided with the formula, is given by the following expression. Okay. And here they have given us the KSP value as well, and they are asking you to calculate the solubility. Okay. So how could you find the solubility? If you recall, let me tell you, for example, if you recall the equation, it's the equation for the dissociation is this, that when it dissociates, it gives you 1 mole of iron 3 positive ions. and 3 moles of hydroxide ions, right? So if there are x moles of this, then this must be 3x, right? So if I substitute these in the equation, the Ksp and minus 39 is 2. Concentration of iron would be x, and concentration of hydroxide would be 3 times 3x cube, right? Yes, is this understandable to everyone?
Yes, sir.
Okay, then it would become 2.0 exponent minus 39 is equals to, if I take the cube of the 3, it would become 27, and x cube times x would be x raised to the power 4. So if I have to find the value of x, then it would be 4 root or tetra root 2.0 exponent minus 39 over 27. So here you will get the value of x, which is equals to the concentration of iron 3 positive ion, and that is also equals to the concentration or the solubility of iron hydroxide. So can you tell me the answer?
Sir, 9.3 into 10 to the power negative 11.
Sorry, can you repeat?
9.27 into 10
9.278 into 10 raised to the power
negative 11.
negative 11, and concentration would be mole per dm cube. So here I normally write in 3 significant figures, so it would become 9.28 exponent minus 11 mole. Okay, the unit is written. Yes, is this understandable to everyone? Yes, if anyone have any doubt in it, kindly ask. Yes, is this clear?
Yes, sir.
Yes, sir.
Okay, let me recall, we equate these two with each other. Why? Because both have a ratio of 1:1. That's why we equate them. Okay, now next part. Calculate the solubility of FeOH thrice or iron 3 oxide in 0.01 mole per dm cube of barium hydroxide. Okay. So what they are actually asking over here, that for example, you have a one solution of barium hydroxide over here, and in that barium hydroxide, the concentration of that barium hydroxide is 0.010 mole per dm cube, right? And what we are adding? We are adding in it iron hydroxide. And they are asking that when it is being added, then afterwards, what is the solubility of iron 3 hydroxide? Is the question is understandable to everyone? Yes. First, tell me the question understandable to everyone.
Yes, sir.
Okay. Now, if you think barium is in group 2 and it's at the bottom of group 2, so it is actually more soluble or highly soluble. And the iron hydroxide is basically the sparingly soluble. Okay, so what would happen over here when there is a aqueous barium hydroxide is already there and we are adding iron hydroxide in it. So this is the solubility of iron hydroxide in water basically. Okay, this is the solubility of iron hydroxide in water. Now, if we are mixing these two, then what would happen? See, actually, we have a iron 3 positive ions in the aqueous state. We have a barium ions in its, sorry, not beryllium, barium ions in its aqueous state. And we have a hydroxide ions in its aqueous state, right? I'm just intentionally not putting a coefficient over here. Okay, so think that the solution is the concentration of the solution in which I am adding the iron 3 oxide is 0.01 mole per dm cube. So it means the concentration of hydroxide ions would be, if we compare it with the barium hydroxide only, so it is twice. Okay, there are twice of the hydroxide ions as compared with the barium. So its concentration would be 2 times 0.010 mole per dm cube. Is this part is clear?
Yes.
That is the concentration of
सर
hydroxide
सर ये
ions.
हाइड्रोक्साइड 2 क्यों होंगे, क्योंकि बैलेंस तो नहीं होंगे, सिर्फ हम बेरियम के साथ देखेंगे.
Yes. Yeah,
और सर वो जो
that
आयरन के
is
साथ है उन वालों का क्या करेंगे?
the solution. No, we are just ignoring that. We are just considering the initial condition that initially in the aqueous solution, initially before putting this one, before putting this,
Okay,
the
okay, sir.
concentration of hydroxide ion is this.
ठीक है. Yes, sir.
Is this understandable? Okay. So now we know the concentration of hydroxide ions. And if we adding the iron, the compound of iron in it, the concentration of iron, there must be some concentration of iron, but we don't know that concentration of iron. So we consider that concentration of iron would be X. So we use the same KSP expression that is used over here, over earlier, that they provided us that the KSP of the is actually equals to concentration of iron 3 positive ions times concentration of hydroxide ions cube. KSP is the solubility product, that is 2.0 exponent minus 39. We don't know the concentration of iron, that how much iron ions are going to dissolve, but we know the concentration of hydroxide in it, and which is actually 2 times 0.010, and I have to take the cube, right? Now, if you will find the value of X over here, so X would be equals to 2 into 0.010 raised to the power 3 divided by 2.0 exponent minus 39. Yes, what would be the value of X?
Sir, 2 into 10 to the power negative 33.
Can you do it again?
Sir, 4 exponent 33.
I don't think so. You are also getting the wrong answer.
सर ये 2 into 10 power negative 39 ऊपर नहीं आना चाहिए क्या?
Yeah. Thank you, Murtaza. So if I'd make the x subject, then it would be 2.0 exponent minus 39 in the numerator and 2 into 0.010 cube in the denominator.
Sir, 2.5 exponent minus 34.
Okay, 2.5 exponent minus 34. So this is the value of x, and x is actually representing the concentration of iron 3 positive ion, and that is the concentration of iron 3 hydroxide in aqueous solution of barium. So the answer would be 2.5 exponent minus 34. Is this clear? Yes.
Sir, can you explain again how we kept the get the concentration of the hydroxide from the barium ions into the iron one?
Can you repeat again?
Like, how did we knew that 2 into 0.01 would be the same concentration for the OH and iron?
Okay. Think. We have just found the concentration over here in the water, right?
Yes.
Is this value is a big enough or a very small value?
Small value.
So if I times it 2, then it would be the value of hydroxide ion in water.
Yes.
So how significant is this when I compared it with this one?
It's still small.
It's very small. It doesn't make any difference because it's just exponent minus 2 and it is just exponent minus 11. So what you would do if there is any so actually this is the concentration of hydroxide ions in water. Now think, there is a hydroxide already present in this solution, right?
Yes.
And I'm going to dissolve the iron 3 hydroxide in it. So would the iron 3 hydroxide would going to dissolve, this amount would be going to dissolve or lesser than this?
Lesser.
Lesser. So it means the hydroxide ions concentration that would be going to be added in this would actually lesser than this value, right?
Yes.
It is even lesser than this value. So if I am ignoring this value, so that doesn't make any difference or any error in my calculation.
Right.
Is this clear now?
Yes, sir.
Because the value is very small, and even when I'm going to add iron 3 hydroxide in a solution containing barium hydroxide, then in this barium hydroxide, then this value even going to be get even more lesser than this one. That's what we know. And if it is even getting lesser than this one, so it is actually very much less significant. So that's why we ignored this value. Instead, we just keep the value of hydroxide ions from the barium only. Is this clear to everyone?
Yes, sir.
Okay. Now, iron 3 hydroxide is less soluble in barium hydroxide. That's why we have figured it out. See, here in water, its solubility is exponent minus 11. But in barium hydroxide, now see, its solubility is minus exponent minus 34, right? So why would this? Yes, I have just discussed. Who is going to tell me the correct reason? Why would this is lower?
Sir, common ion effect.
Have asked just the name of this effect. So yeah, it's a common ion effect that the barium hydroxide already contained the hydroxide ion. That is the common ion that is in the iron 3 hydroxide as well. And due to this common ion, the solubility of iron 3 hydroxide is further lowered. Okay. Now, the numerical value of Ka of HbRO is 2 exponent minus 19. So it means that it is actually calculated. It is a Ka value which is actually calculated by the concentration of hydrogen ion squares over concentration of acid, or it is calculated by concentration of hydrogen ion into the negative ion concentration divided by the concentration of an acid. Okay, X is a solution of HbRO, okay, which contains 4 exponent minus 3 moles of HbRO in 100 centimeter cube. Okay, so these are the moles and this is the volume. These are the moles and this is the volume. In this solution, the following equilibrium is established, okay, in which there are two conjugate acid-base pair. Define the term conjugate acid-base pair. So what is the difference in an acid and its conjugate base? Yes, can anybody identify? If you see, isn't it an acid because it is losing the hydrogen ion? So this one is its conjugate base, right? And if you look at this one is a base. This one is a base. And why? Because it is accepting the H positive ion. So the species that by accepting the H positive ion is a conjugate acid, right? So if you compare or if you relate one pair which is mentioned by the yellow, what is the difference between these two? Or if you relate the two which are mentioned by the purple, what is the difference between these two?
There's a difference of a hydrogen atom.
Of a hydrogen ion, not an atom.
Sorry.
Here the hydrogen ion is being released from this one, and here the hydrogen ion is being added to this one. So that's how you can define the conjugate acid base pair, that conjugate acid base pair are two species that have a difference of one each positive ion only. Is this understandable to everyone? Yes, is this clear?
Yes, sir.
Okay. Just give me a minute, please. Just need 1 minute. Now, next part. Identify the two conjugate acid base pairs shown in the equation above. Okay, see. So we have already figured it out. One with the yellow and one with the purple one. So it means that HbRO is an acid and its base is BRO negative, right? And the in other pair, the acid is H3O positive and the base is H2O. Right? Is this clear?
Yes, sir.
Okay. Now, calculate the pH of solution X, show all your working. Okay, if you recall, X is the solution of HbRO. If you see over here, its volume is 100 centimeter cube. And the moles of HbRO in that are actually 4 exponent minus 3. And the volume is 100 centimeter cube, right? And K is 2 exponent minus 9. The Ka value of HbRO is 2.00 exponent minus 9, right? So if you recall, the core formula or the basic formula of finding the pH is actually pH is equals to minus log concentration of hydrogen ions, right? And it's a weak acid, so we don't know the concentration of hydrogen ions. So we have to figure out the concentration of hydrogen ions. And for finding that, we are given with the concentration of Ka, value of Ka, and we know the volume and the moles of HBRO, so we can find the moles concentration of HBRO as well. So for that, we can use this expression that the concentration of hydrogen ion square divided by concentration of HBRO. From this, we can get the concentration of hydrogen ions. And to find the concentration of HBRO, it is not provided over here, but we can find it by dividing the moles of HBRO over volume of HBRO. Now, these three expressions or the formulas can be used in the reverse order, which means first I would do this, then I would use this formula, and then I would use this formula to find the pH. Is this understandable to everyone? So first find the concentration of HBRO. That is equals to moles of HBRO, which are 4.00 exponent minus 3. Volume is 100 centimeter cube. That must be divided by 1000 to convert into decimeter cube. So can anybody tell me the value, the concentration of HBRO?
0.04.
0.04 mole per dm cube. So first what I did, I uses the expression which I mentioned 1. Now I'm going to do the expression 2. The K value is 2.00 exponent minus 9, sorry, is equals to square of the concentration of hydrogen divided by the concentration of HBRO that just I have found in the previous step. It is 0.04, right? So to find the concentration of hydrogen ions, it would be square root of 2.00 exponent minus 9 times 0.04. Can anybody tell me the answer?
Say 8.9 exponent minus 6.
8.9 exponent minus 6. Yes, then you have a one question. 8.9 minus 6. Is this Rida?
Yes, sir.
Okay. See, then, when you dissociate HBRO, it dissociates into hydrogen ions and BRO negative ions. So if I write the K expression would be equal to concentration of hydrogen ions times concentration of BRO negative ions divided by concentration of HBRO. But see, the ratio of hydrogen ions and the BRO negative ions are the same. So it means the concentration of hydrogen ion is exactly equals to concentration of BRO negative ion. That's why in this expression, what we did, we equated the concentration of BRO ion with the hydrogen ion. So that's why it gets hydrogen ion square divided by HBRO. Concentration of HBRO. Is this clear then? So that's why it gets square of the hydrogen ion concentration. Okay, so we got the concentration of hydrogen ion. Now I'm going to use the equation, the expression that I have pointed third step, that is pH is equals to minus log to the base 10 of the concentration of hydrogen ion, which is 8.9 exponent minus 6. So can anybody solve in the calculator and tell me the answer?
5.05.
5.05. So here we go. Yes, if anybody have any doubt in this part, kindly ask. Okay, now, interesting. A solution containing 2 exponent minus 3 moles of sodium hydroxide is added to solution X. A buffer is formed. Calculate the pH of buffer solution. Yes. Concentrate NaOH, when we have added to HBRO, they are going to react forming NaBRO and water, right? The equation is balanced. There is no need to balancing. Okay. Now think, at initially, the moles of HBRO are actually 4.00 exponent 3 minus 3. And the moles of sodium hydroxide that we have added is 2.00 exponent minus 3. And initially, these two are, they have a no amount. These are 0. So what would be the change? If you see, both have a ratio of 1:1 according to the balance equation. And if we see the sodium hydroxide that we have added is lesser in amount, so it means all of the sodium hydroxide is going to be consumed. That would be the change. And at equilibrium, there would be 0 moles of sodium hydroxide in the solution left. That is clear to everyone? Yes? If anybody have any doubt in this part, kindly ask. Is this clear to everyone?
Yes, sir.
Now, as the mole ratio of sodium hydroxide and HBRO are exactly same, and if there are 2 exponent minus 3 moles of sodium hydroxide is consumed, then exactly the same moles of HBRO would also be consumed. So at equilibrium, we are left with 2 exponent minus 3 moles of this acid, and we know this is a weak acid, right? Now, the change that observed at the product side would be positive 2.00 exponent minus 3 for NaBRO and positive 2.00 exponent minus 3 for water as well. So it means at equilibrium, we would get 2 exponent minus 3 moles of NaBRO and 2 exponent minus 3 moles of water. So this is the conjugate base or the salt of that weak acid, right? So in the mixture, as these two are present, so it means now this solution becomes buffer. And in that buffer solution, when the solution is become buffer, now the moles of HBRO, that is the weak acid, is 2 exponent minus 3. And the moles of the salt, that is NaBRO, is 2 exponent minus 3 as well. Is this understandable?
सर आप ये दोबारा एक्सप्लेन कर देंगे?
Okay, what is the confusion over here, Saliha? First tell me this. What part of this you didn't understand?
आपने आइस टेबल क्यों ड्रॉ किया?
The thing is that if you see, we all know that X is HBRO, right?
Yes, sir.
And its moles are 4 exponent minus 3, right? Is this clear?
Yes, sir.
Now think, how many hydrogen ions are over here? Yes. How many hydrogen ions are over here? Yes, Solia. Are there 1 hydrogen ions in HBRO?
1.
1. And we are adding sodium hydroxide, and in that sodium hydroxide, there is 1 hydroxide as well, right?
Yes, sir. तो वो water बनता है.
Yes. So that, but think that the moles of HbRO is 4 exponent minus 3, and the moles of sodium hydroxide is 2 exponent minus 3. So it means it clearly indicating that all of the acid was not going to be consumed and some of the acid would left.
Yes, sir.
And when a acid that reacted with the base, that acid is going to form the salt.
Yes, sir.
So in the mixture, when the reaction is finished, we have a weak acid present in it, and we have its salt is also present in the mixture, right?
Yes, sir.
So what is buffer? If you recall the definition, if you recall the composition of a buffer, it says that it is a mixture of a weak acid and its salt, right?
Yes, sir.
So that's why I draw the ice table to make you all understand that why we are considering it is a buffer, because we are just adding the base and the neutralization is taking place. But it becomes buffer because when the reaction is finished, there is a weak acid left in the mixture and we have its salt as well. But for example, if I have this solution and here I have a acid already present in it and it's a 4 exponent minus 3 moles, right? And if I put a sodium hydroxide in it and I put exactly 4 exponent minus 3 moles of sodium hydroxide in it, then the complete neutralization would occur. And in this case, no buffer would form because at the end of the reaction, we are left with the salt in the mixture. There is no acid left behind. Did you understand this?
Yes, sir.
But for example, if I have another container, in that container, I have already a HbRO and its moles are 4 exponent minus 3. And now I am putting sodium hydroxide, but I just put the sodium hydroxide, the moles of sodium hydroxide that I put over here are 3 exponent minus 3. So it means that when the reaction would end, we are left with the acid and its salt both, right?
Yes, sir. Correct.
So it means there must be a buffer over here. So this solution becomes buffer. So we got the buffer, and in that buffer, we know that what are the moles of acid and what are the moles of its conjugate base. Is this clear to everyone? Yes. Okay. Now, if you recall the pH expression for the buffer, it is basically, if you recall, pH is equals to pKa plus log 10 to the concentration of salt over concentration of acid. This is the expression for finding the pH of a buffer solution, right? And if you recall, we discussed one more thing in our lectures, that when the concentration of salt is actually gets equals to the concentration of acid, in that case, that pH is actually equivalent, becomes equivalent to pKa. So it means that if you see, we are provided with Ka, value of HbRO. So this would help me to identify the buffer, the pH. So if I have to find the pH, what I would do, it would be equals to minus log of Ka in this case. And then it would be minus log 10 of 2.00 exponent minus 9. If you would solve, you will get the pH of the buffer. This is the case when with the concentration of salt and acid are gets equal, then pH becomes equals to pK. Okay. So for pK, I have to take the minus log of Ka. So if I take the minus log of 2 exponent minus 9, which is the Ka value, so I will get the pH. Can anybody tell me the answer?
Sir, 8.699.
It's 8.699, which would means that it would becomes equals to 8.70. Is this clear now? If anyone have any doubt, do ask. Okay. Now, question number 6. Copper is a transition element. It forms a wide variety of compound. Define transition element. Now
सर
I'm not. Yes.
सर इससे ऊपर वाले में हम लोग डायरेक्ट मोल रेशियो लगा के नहीं कर सकते?
Yes, it can be done, but I uh, do the long way to make you understand that why it's happening. You can do it that way as well, but it might not be understandable for everyone. Okay.
सही है सर.
So it's a definition, and we have discussed definition so many times, so I'm skipping the definition. An aqueous solution of copper 2 sulfate contains hexaaqua copper ions, copper 2 ions. If an excess of concentrated hydrochloric acid is added to this solution, a ligand exchange reaction occur and CuCl42 negative is formed. If you recall, there are 6 ligands, so it means its shape would be octahedral over here. And there are 4 chloride, and in case of a chloride, the shape would be tetrahedral. I hope everybody remember this. Complete table 5.1. State the geometry. Okay. The coordination number of copper and one bond angle in each of the two angles. So if geometry we just discussed, here the geometry would be octahedral, and here the geometry would be tetrahedral. As 6 monodentate ligands are attached, so the coordination number is 6. 4 monodentate ligands are attached, so the coordination number would be 4. Okay. And the bond angle, in octahedral case, the bond angles are 90 degrees. And in tetrahedral case, the bond angle is 109.5 degrees. Is this clear? And I think it's not question number 6. Wait.
It's
Yeah,
question number 5.
Yeah, it's question number 5. Okay. Now, an isolated copper 2 positive ions in the d orbital are all degenerate, means having same energy. In complex ions such as hexaaqua copper 2 ion, the d orbitals are non-generate, which means splitted into 2 different energy levels. Define degenerate and non-degenerate in the context. Okay, we just discussed. So it is used for same energy, and non-degenerate used for different energy. Now, explain why the solutions of the 2 complex ions in table 5.1 show different colors. So the reason is that, if you recall, the color is shown by the absorption of the photon or the wavelength or the frequency. So it means they are going to absorb different photons or the different frequency or the different wavelength. So it is because both the complex ions absorb different wavelength or different radiations or different photon. Okay, next part. Cu2 positive forms a complex ion containing water molecule and ethane diode molecule as a ligand. If you see, you must remember that it's a bidentate ligand. The formula of the complex is C2O42 and H2O2. The ethane diode is a bidentate ligand. Okay, what is mean by the bidentate ligand? The one which forms two dative bonds. Okay, ligand which forms two dative bonds. Now, okay, there are three stereoisomers with the formula of this. Complete the three-dimensional diagram, show these three stereoisomers. So, let me recall you. First, make the bonds. Then we will discuss how these three isomers would form. And these are the stereoisomers. So when this is the case, if you recall, there are two bidentate ligands and two monodentate ligands, then the cis and the trans isomer is formed, and the cis isomer had its optical isomer, means mirror image. So this is the complex, right? And if you recall the formula of C2O4, so C2O4 would be O, C double bond O, then C double bond O, and then O. These two O are negatively charged, and from where the ligand attaches. So let me draw over here. For example, I am keeping the two chlorines to the 90 degree. That's make it cis. And here I am making the two chlorines at 180 degree. This makes it trans.
सर क्लोरीन तो नहीं है वाटर है
Yeah, sorry. Yeah, the monodentate ligand is water. So if I'm putting the two water ligands at 90 degree, then it is cis. And if I'm putting the two water molecules at 120 degree, 180 degree, then it's trans. Now I'm left with the other ligand. So what I do, I put two O like this, then C double bond O, C double bond O, and this one ligand is attached, and then 2O, a carbon, both carbons are joined and both have a C double bond O. So see, a cis isomer is formed. Now for trans isomer, both the oxygens on the neighbor bonds, then each oxygen is bonded with the C, and both the C's are joined with each other, and then each C have a one oxygen with which it is forming a double bond. Then on the opposite side, we would do the same thing, two oxygens. Both the oxygens would bonded with the carbon, and these two carbons would bonded with each other. Then a double bond O on one carbon and the double bond O on another carbon. So this is a trans. Is this clear? Now, for this cis one, what I have to do, I have to make its mirror image. So how would I make its mirror image? You can make the mirror image by keeping the first orientation in front of it and just try to make its mirror image. So if I would if this is the plan and this is a plane, and I would trying to make its mirror image. So see, I would put one O over here, one O over here, then C double bond O, C double bond O, and this. And in the same way, one bond O over here, one O over here, C, C, and both the C have a double bond O, and both the water on the opposite side. So that is the third isomer, which is actually, when I relate these two, I consider them optical isomers. And when I relate these two, I consider them geometrical isomers. Is this understandable to everyone?
Yes, sir.
Okay. Now, use your answer to C2 to answer this question. Okay. In C2, we have drawn the isomers. Stereoisomer 1, 2, and 3 show two different types of isomerism. Name these two types of isomerism. For each type of isomerism, identify the pair of stereoisomers that demonstrate this isomerism. Okay. So we just figure it out. One is geometrical, and the other one is optical, right? And for geometrical, which two pairs are geometrical? The stereoisomer 1 and 2 are geometrical, and the stereoisomer 1 and 3 are optical. Is this clear to everyone?
Sir, do we
Yes.
have to make the sir, do we have to make the bracket and write the charge?
Yes, there. Yeah. So it's better to always enclose in bracket and put a charge if there is a net charge. Thank you, Rafael. Now, next part. A solution contains 3.70 gram of this complex dissolved in 100 centimeter cube of a solution. Okay. So the mass of this complex is 3.70 gram and the volume of the solution is 100 centimeter cube. A 25 centimeter cube sample of this solution, okay, is warmed and oxidized by 0.1 mole per dm cube acidified potassium manganate. This is the reaction, okay. So in this reaction, if you see, according to the data provided, we have used 25.0 centimeter cube of this solution. And it is taken out from the initial solution whose volume is 100 centimeter cube. And in that 100 centimeter cube, 3.70 gram of the sample is dissolved. And we use manganate ions. We don't know its volume, but we know the concentration of these manganate ions, that it is 0.0100 mole per dm cube, right? Calculate the minimum volume of 0.011 mole per dm cube potassium manganate. Okay, we have to find the V volume of this one. Needed to oxidize all the ethane diode ions in 25 centimeter cube sample. Show all your working. Okay. So see, the MR is provided over here. So from this MR, I can find the moles of this complex. The moles of this complex would be equal to its mass, that is 3.70, divided by its MR, that is 321.5. Can anybody tell me the moles?
Sir, 0.1151.
0.
1151.
Are you sure these are the number of moles?
So 0.0115.
Okay, yeah, because see, it's just one decimal place, and here we have a 3 decimal place, so it would be 0.0115. Okay, that's correct, probably. So 0.0115 are the moles of this whole complex, right? In this whole complex, see how many ethanoate ions are there? Yes?
So
How
2.
many 2. So it means moles of ethanoate ions would actually be equal to twice of these moles. Yes, can anybody tell me the answer?
So 0.023.
0.023. These are the moles of ethanoate. But my question is, can anybody identify in how much volume these moles are present?
Sir, 100 centimeter cube.
Yeah, 100 centimeter cube, because we have dissolved it in 100 centimeter cube. So these are in 100 centimeter cube. So we have used 25 centimeter cube from that 100 centimeter cube. So in 100 centimeter cube, if I have this much moles of ethanoate ions, then in 25 centimeter cube, the number of moles of ethanoate would be X. So X would be equals to, just times it. No, sorry. Divided by 4. Yes, can anybody tell me the answer?
Sir, 5.75 exponent minus 3.
5.75 exponent minus 3 are the moles of ethanoate ions in 25 centimeter cube. Is this clear to everyone? If anyone have any doubt, please ask before I would proceed further. Yes. Okay. Now, if you look at the equation between the ethanoate ions and manganate ions, their moles ratio would be 2:5. So if this is the number of moles of ethanoate ions, then the moles of manganate ion would be X. So here X would be equal to 5.75 exponent minus 3 times 5/2. Now, can anybody tell me the answer of?
सर रेशो उल्टा लिख दिया आपने.
1 minute. No. It's
Sir,
correct.
0.014.
5.75 into 5 रेशियो उल्टा है.
Yes, sir.
C2H4 का
MnO4
5 है.
minus के 2 moles.
It's 5 and it's 2. So here 2 and it's 5. Okay, thank you. I didn't look at the equation. There are 5 moles and there are 2 moles. Okay. Yes.
Sir, 2.3 exponent minus 3.
2.3 exponent minus 3. These are the moles of what? Manganate ions, right? And we know the concentration of manganate ions that it is provided over here. If you see, this is the concentration, which is 0.0100 mole per dm cube. So the formula is concentration is equals to moles over volume. So if I have to find the volume, then volume is equals to moles upon concentration. Moles are 2.3 exponent minus 3 divided by concentration, that is 0.01. Yes. It's 0.23. Okay. Thank you, Sarah. It's in dm cube. And here we need in centimeter cube. So we have to multiply it with 1000 to turns into centimeter cube. So 1, 2, 3. So it would be 230 centimeter cube. Is this clear? Yes.
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 Okay. Now, copper 2 nitrate and barium nitrate both decomposes when heated. Copper 2 nitrate decomposes at a lower temperature than barium nitrate. Suggest a reason for this difference. Explain your answer. Yes. Who can recall this? Yes.
सर
पोलराइजेशन
कॉपर का रेडियस बेरियम से छोटा होता है.
Yes. If it's a lower decomposition occurring as lower temperature, which means that nitrate ion is more distorted, and if it's more distorted, which means that the cation is smaller. So that is the reason. So here I can write that copper nitrate is decomposing at the lower temperature. So I would write that copper 2 positive ion is smaller than barium 2 positive ion. So copper 2 positive ion polarizes or distorted nitrate ion more, hence the nitrogen oxygen bond gets more weaker in copper nitrate. Is this clear? Yes. Is it clear to everyone?
Yes, sir.
Okay. Now, question number 6. Okay. An aqueous solution of cobalt 2 chloride is pink color due to the presence of hexa-aqua cobalt 2 complex ions. Table 6.1 describes what is observed when the named reagent is added to an aqueous solution of cobalt 2 chloride. Okay. So the color would be actually the same as when we do these two with the copper. So when I add sodium hydroxide in a copper, what would happen? A blue precipitates would form. So in the same way, here, the product containing cobalt would have a blue color, and it's a precipitate, so its state would be solid. And then when we add a constant, okay, let me do over here. When I add NaOH, it would become COH2O4 and OH twice. It must be in a same line. And it's a solid, which shows blue precipitate. Okay. But when I add HCl in it, it would turn into CuCl4, 2 negative, and it's aqueous, and 6 water molecules are released, and it's of blue color again. So blue, and the state would be aqueous. Okay.
Sir, won't it be dark blue?
No, dark blue is the case for ammonia. When we add ammonia in the copper and excess ammonia is added, then the deep blue solution or dark blue solution is formed. In the same way, when we add excess ammonia in cobalt, we would get a dark brown solution over there. Okay, so they have asked for the equation. We already did over here in some sort. So equation would be cobalt hexa aqua complex reacting with NaOH as 2 hydroxide ion are in the complex. So I just write 2 hydroxide ions and then cobalt H2O4 as two hydroxide ion are getting added, so the whole complex becomes neutral and two water molecules. In this case, cobalt H2O6 with two positive charge, 4 chloride ions forming CO, Cl4 2 negative, and 6 water molecules. Okay. Define the stability constant. We have discussed it previously as well. So it is the equilibrium constant for the formation of complex ion in water, which is actually acting as a solvent over here. Write an expression for the stability constant of K stab of this. Okay. So if it's in a water, so initially it have the initial complex would be the one having a water in it. So this would be your product. So I would write it in the numerator for a K stab expression. And over here, I would write the water complex. And along with that, ammonia raised to the power 6 because 6 moles are being substituted. Now they are asking to give you the units. Okay. So, okay, make one more square bracket for the concentration. One is for the complex. Okay. So above in the numerator, we have a 1 concentration. So it is mole per dm cube. In the denominator, we have a 1 concentration of the complex, that is mole per dm cube, and 6 is raised to the power 6 concentration of ammonia. So mole per dm cube raised to the power 6. These two are actually cancelled out. So we are left with 1 over mole raised to the power 6 and dm minus 18. So when I put it in the numerator, it would become mole raised to the power 6 and dm raised to the power 18. Is this clear to everyone?
Sir.
Yes, sir. Okay. Now, the numerical value for K step of hexaamine cobalt 2 complex ion is 7.7 exponent 4. In an aqueous solution, the concentration of cobalt hexaamine 2 complex ion is 0.074 mole per dm cube. Okay, its concentration is this, and that is its K step. The concentration of ammonia is 0.48 mole per dm cube at equilibrium. Calculate the concentration of this. So see, if you see, you are provided with this K step value, you are provided with this value, and you are provided with this value, and you have to find this one over here. So just put the values over here. K step is 7.7 exponent 4 is equals to concentration of hexaamine cobalt complex is 0.0740 divided by x that I have to find, multiply by 0.480 raised to the power 6, because it's raised to the power 6. So if you would find x, so x would equals to 0.0740 over 7.7 exponent 4 times 0.480 raised to the power 6. So can anybody calculate and tell me the answer?
So 7.86 into 10 to the power negative 5.
Okay, so 7.86 into 10 raised to the power negative 5. 7.86 into 10 raised to the power negative 5. Is this clear to everyone?
Yes, sir.
Okay. Now we are left with 3 questions from this paper. And now our next session will be on Sunday, not tomorrow, and no any session today. But we will keep multiple sessions on Sundays and multiple session on Monday. So by Monday, we are going to finish the February-March 2023 as well. Okay. So I will share the timings with you. We have to finish 2023 Feb-March by Monday. Because I think some of you have a paper on 3rd of March as well. So this is our target. We will keep sessions on Sunday and Monday. And let's see if I get a time. So probably we will keep session tomorrow as well, but I'm not sure. Okay.
So can you also send the paper on the group?
Yeah, I will be sending in the paper, inshallah, today.
Okay, thank you.
Okay. Take care, everyone. Allah Hafiz.